This video covers section 1 of chapter 2, where we're going to start getting into linear equations. In chapter 1, we were working with expressions. Now we're going to switch to equations. So what exactly is an equation? An equation is a statement of equality between two expressions. So if we have two expressions and we put an equal sign between them, we have an equation. For example, we could have the expression 3x and the expression 12. Put an equal sign, now we have an equation. Another example might be 13 minus x equals 2. That would be an equation with two expressions that are equal. Or even 4 times x plus 3 equals 2x times 1 plus x. All of these are examples of equations. I just have two expressions that are equal to one another. Now, a linear equation is a specific type of equation. A linear equation in one variable has a single variable, and the exponent for that variable is 1. That is, if our variable is x, then our equation can only have x in there, not an x squared, not an x cubed, not a square root of x, nothing like that. There's a single variable, and the exponent for that variable is just 1. A solution to an equation is a value that when you substitute it in for the variable, you get a true statement. So we say that a value is a solution to an equation if we put it in there for x and the result is something true. Let's look at example 1. In example 1, we're asked to find out if the given value of x is a solution to the given equation. In part A, we're given that x is equal to -7, and our equation is 4x plus 23 equals -5. So we're going to take that equation, 4x plus 23 equals -5, and we're going to substitute in place of x the value -7. So instead of 4 times x plus 23, we have 4 times -7 plus 23 equals 5. Now the question is it a solution? Does this produce a true statement? Using good order of operations on the left, we'll start by multiplying 4 times -7, which is -28. And then we can add. We have -28 plus +23, giving us -5. At the end, we end up with -5 equals -5, and this is in fact a true statement. So what does that mean? That means that -7 is a solution. -7 is a solution to the equation 4x plus 23 equals -5. Let's look at part B. In part B, we're given an x value of 5 and an equation of 3 minus 2x equals 13. So we're going to take that equation 3 minus 2x equals 13, and we're going to substitute in for that x the value 5. So where that x is, I'm going to put 5. So instead of 3 minus 2x, we now have 3 minus 2 times 5 equals 13. Using good order of operations, we need to multiply -2 and +5 together first to get -10. So we have 3 minus 10 equals 10. Finally, we can subtract. +3 minus 10 is -7. So at the end, we end up with -7 equals +10. That is not a true statement. This is not true. So that means that 5 is not a solution. 5 is not a solution to the equation 3 minus 2x equals 13, because when we substituted in for x, we did not get a true statement. I'm going to leave C and D for you to work on by yourself, and I'm going to go on to our next definitions. We were just working on determining if a certain value is a solution to an equation. When you have a set of all solutions to an equation, it's called that equation's solution set. We're going to use the notation with our curly brackets that we've seen before. We will list all of the solutions to an equation inside of these brackets to denote the solution set to the equation. Now, the process of finding all of the solutions to a given equation, that's called solving the equation. So when you're given an equation and asked to solve, you're asked to find all of the solutions to that equation. Let's take a look at example 2. In example 2, we're asked to solve, so we're going to find all of the solutions to the equations, and we're going to use the multiplication property of equality. So what does that mean? What that means is if I have two expressions, A and B, and they are equal to each other, so expression A equals expression B. The multiplication property of equality tells me that I can multiply both sides of this equation. I can multiply both expressions by any non-zero number. That is, as long as n is not 0, we can multiply both sides of an equation by the same number, and we don't change the equation. It's still the same equation. Let's use this technique with example A. In example A, I have x over 8 equals -2. I have two expressions, x over 8 and -2, set equal to one another. Now, I'm trying to solve. I'm trying to find the solutions to this equation, the values for x that make a true statement. What I would like to do is I would like to get x all by itself so that I know what it is equal to. Right now, x is being divided by 8. I have x over 8. What's going to help me out is multiplying both sides of this equation by 8. The multiplication property of equality tells me I can do this. 8's not 0, so I can multiply both sides of this equation by 8. Now, on the left side, I have an 8 in the numerator and an 8 in the denominator. That is, 8 goes into 8 one time and 8 goes into 8 one time. So that becomes 1 times x, or just x. On the right side now, I have -2 times +8, or -16. Now I know that x is equal to -16. The last thing to do here is to double check our work. Check that answer. Let's take -16, put it back into our original equation, and double check that it works. So instead of x over 8, I'm going to write -16 over 8 equals -2. -16 divided by 8 is -2. And we have a true statement, so our solution works. Writing the solution in set notation, we have a solution set containing the one value, -16. I'm going to leave part B for you to try, and I'm going to go on to example 3. Notice that example 3 has the same instructions. We're going to solve the equations, and we're going to use the multiplication property of equality. That means we're going to multiply both sides of the equation by a non-zero number that's going to help us isolate that variable, help us solve for that variable. Let's look at part B. I'll leave A for you. In part B, I have 7 times B equals -84. In our previous examples, our variable was being divided by something, and so we multiplied to clear it. Now on this one, my variable B is being multiplied by 7. To undo that, I would like to divide by 7 to cancel those out. Now, why does that work with the multiplication property? The multiplication property would tell me that I can multiply by 1 over 7 on both sides of the equation. That's the same thing as dividing by 7. By multiplying both sides by 1/7, I have these two 7s simplifying to 1, leaving me with just B on the left side. On the right side now, I have negative 84 times 1 over 7. That's negative 84 divided by 7. 84 divided by 7 is 12, so negative 84 divided by 7 is negative 12. Let's take a minute to double check our answer. Back to the original equation, we have 7b equals negative 84. But I'm going to substitute negative 12 in place of b and make sure I get a true statement. 7 times negative 12 is in fact negative 84. So this makes a true statement and our solution checks out. That means that the solution to this equation is just negative 12. And we would write the solution set like this. Our brackets with only the solution of negative 12 inside. I'm going to leave part C for you and go on to part D. Part D, I have negative 8m equals negative 48. Now let's think about what we could multiply both sides of the equation by or divide both sides of the equation by to help us get m by itself. Right now, m is being multiplied by negative 8. So to undo that, I would like to divide by negative 8. Make it fair. Do the same thing to both sides of the equation. Now I have a negative over a negative, which makes a positive. And I have 8 goes into 8 one time, 8 goes into 8 one time. Those simplify to 1. So now on the left side, I have 1 times m, or simply m. On the right side, I have a negative over a negative, and 2 negatives make a positive. That leaves me with 48 divided by 8, which is 6. Let's take a brief moment and double check our answer. Substituting 6 for m, we get negative 8 times 6 equals negative 48. Negative 8 times 6 is negative 48. So this makes a true statement and our solution checks out. So the solution set for this equation is the set containing the single value 6. Let's look at E. E might look a whole lot different, but we're going to use the same process. In part E, I have 9 over 16x equals 21 over 8. Let's think about what's happening to our x right now so that we can try to undo it. Right now, x is being multiplied by 9 over 16. You could think of that as x being multiplied by 9 and divided by 16. So the opposite of that would be multiplying by 16 and dividing by 9, or multiplying by 16 over 9, or multiplying by the reciprocal of 9 over 16, flipping it over. Make sure you make it fair and do the same thing to both sides of the equation. Now I have a 16 in the numerator to simplify with a 16 in the denominator. I have a 9 in the numerator to simplify with the 9 in the denominator. That leaves me with 1 times x on the left, or simply x. On the right, we can also do some simplifying before we multiply. Look at 21 and 9. Those are both multiples of 3. 3 goes into 21 7 times, and 3 goes into 9 3 times. 8 and 16 are both multiples of 8. 8 goes into 8 one time, and 8 goes into 16 2 times. That means we are left with 7 times 2 over 1 times 3, or just 3 in the denominator. 7 times 2 is 14. 1 times 3 is 3. So we have a solution of x equals 14 over 3. Let's double check. Substituting in x for 14 over 3, we have 9 over 16 times 14 over 3 equals 21 over 8. Simplifying on the left side, 3 goes into 3 one time, 3 goes into 9 3 times. With 14 and 16, we could divide both of those by 2. 2 goes into 16 8 times, and 2 goes into 14 7 times. This leaves us with 3 times 7 in the numerator and 8 times 1 in the denominator. 3 times 7 is 21. So we do get 21 over 8 equals 21 over 8. That is a true statement, so our solution of x equal to 14 over 3 works. And we would write our solution to the equation as the set containing the single value of 14 over 3. I'm also going to leave part F for you to try out on your own. I'm going to go on to example 4. Example 4 also asks us to solve, but this time we're going to use the addition property of equality. Let's talk about what the addition property of equality tells us. If we have two expressions, A and B, and they are equal to one another, the addition property of equality tells us that we can add a value to both sides of the equation, and we will not have changed the solutions to the equation. We can add the same number to both sides. I'm going to start by going to part C and let you come back and try parts A and B. The important thing to remember here is that we can add the same number to both sides of an equation. In part C, we have negative 13 equals x minus 28. Right now I have x and I'm subtracting 28 from it. The opposite of subtracting 28 would be adding 28. So I'm going to add 28 to both sides of my equation. I also want to show you a way that I tend to write this. I like to write plus 28 underneath both sides because then the addition process becomes a little more clear to see. However, writing it the first way is not incorrect and you are more than welcome to do that. Adding 28 on the left side gives us negative 13 plus 28, or positive 15. On the right side, I have x minus 28 plus 28. Well, a negative 28 plus a positive 28 is 0, so this becomes x plus 0 on the right side, or just x. This tells us that x is equal to 15, and the last thing we need to do is to double check. Substituting 15 in where the x is, we have negative 13 equals 15 minus 28. 15 minus 28 is negative 13. So we do end up with a true statement and our solution works. That is, the solution set for this equation is the set containing the single value of 15. In part D, we have 5 equals x plus 19. Right now, I have 19 being added to x. The opposite of that is subtracting 19. Now remember, we have the addition property, but think about this for a moment, that adding a negative 19 is the same thing as subtracting 19. So the addition property also lets us subtract the same number from both sides of an equation. So to get rid of that 19, we're going to subtract 19 from both sides of the equation. This gives us 5 minus 19, or negative 14 on the left. This gives us x plus 19 minus 19, or x plus 0. That is, x equals negative 14. Let's double check. Substituting negative 14 for x, we have 5 equals negative 14 plus 19. On the right side, we have negative 14 plus 19, which is in fact positive 5, and we have a true statement. Writing this in set notation, our solution set is the set containing the single number negative 14. The last thing we're going to do is a couple of word problems in example 5. Part A says that Josh spent a total of $26.50 to take his date to a movie. This left him with only $38.40 in his pocket. How much money did he have with him before going to the movie? First, let's write this in words and set up an equation. Then we can substitute in what we know and a variable for what we don't know. We know that Josh started out with some starting amount of money. Then he took someone on a date. That means he subtracted money from his starting amount. At the end of the night, he had money left over. Now, let's fill in what we know. We know that he spent $26.50 on the date. We also know that he had $38.40 left in his pocket. Now, we almost have our equation set up. What we don't know is the starting amount. That's exactly what we're asked to find. How much money did he have with him before going to the movie? The starting amount. Let's use a variable to represent that. I'll choose x. So now we have the equation x minus $26.50 equals $38.40. To solve this, we can add $26.50 to both sides to use our addition property of equality. A negative 2650 and a positive 2650 is 0. So that leaves us with x plus 0, or just x on the left side. On the right side, we have $38.40 plus $26.50 for a grand total of $64.90. So he must have started with $64.90, spent $26.50 on the date, and then was left with $38.40 in his pocket.